Hello and welcome. My name is Eric Müller, and today I will be talking about a classroom example with MATLAB focused on learning for fluid property correlations. So to start, I'd like to give a little bit of background and motivation for this exercise. This exercise is aimed at first-year engineering students and has been tested with undergraduates at Imperial College London. In this case, students are enrolled in a mandatory 6 weeks hands-on introduction to programming in MATLAB course. This course is completely practical in nature. It's a pass-fail module, and it's given at the start of their entry to the department. The course covers the basics of programming in the first 3 weeks, and then in the next 3 weeks starts focusing on skill sets which they may need in the rest of the Chem curriculum, including simple things like plotting and going towards solution of linear sets of equations, solutions of ordinary differential equations. But we saw there was a pressing need, and actually there was a request from the students to be introduced to some of the basic notions of machine learning. So this is where this exercise comes in. So the challenge that is given to them at the end of the MATLAB, near the end of the MATLAB course, is the following. You are given a very large table of physical properties for many organic substances. This is an Excel sheet, basically an Excel sheet with over 5,000 entries. And they're asked to produce an engineering quality correlation for the boiling point. Of course, boiling point is one of the entries in the Excel sheet, and there's other types of properties, critical properties and general properties. The Excel sheet is enormous. Opening it up takes quite a while on anybody's laptop, and trying to scroll through it is a reasonable nightmare. So doing anything by hand is really not possible. Everything has to be done through a computer program. The first task that there's put through is to think a little bit about how their correlation should be. And from high school chemistry or just basic knowledge of physical chemistry, one might think that the boiling point is somehow proportional to the molecular weight. And many examples come to mind, and this one here is a very simple example of how we increase the molecular weight of an organic molecule, and by doing that, we increase its boiling point. So the first suggestion is, why not take this as a starting point? What will happen if we plot, for example, the boiling point as a function of the molecular weight and try to pass a straight line through it? And this is something that the students at this point can do reasonably well with their knowledge of numerical techniques and MATLAB. And when they do that, they end up with a curve that looks like this. The correlation factor is terrible, and the observation of the graph immediately points out that it's not really a very good fit. There is an obvious trend. There is some sort of relationship between boiling point and molecular weight, but clearly that is not the only part of the picture. And if you start playing with it and trying other types of fits, a logarithmic or a square or a quadratic fit, you might be able to improve a little bit on the R squared, but in general, you will not be successful, and it's kind of obvious from the fit. So the next step is to think about other properties which could be of interest. And the students are led to think about the eccentric factor as an alternative. The eccentric factor, as you remember, is basically a point in the vapor pressure curve, so it's not surprising that it will have some sort of relationship. But in practice, the eccentric factor does give a measure of the non-ideality of molecules and the deviation from simple ideal noble gas behavior. And the examples given here, methane and water, are classical, two molecules which are reasonably similar in terms of their size and their morphology, but have widely varying boiling points, of course, the reasons for that are long and extensive. But we can look at the eccentric factor and see that the eccentric factor is somehow picking this up. So students are then led to the suggestion that we might be able to do a multivariate correlation, that we might be able to take the boiling point as a linear function of both the molecular weight and the eccentric factor with 3 parameters, theta 0, 1, and 2, which are somehow unknown. And this is an idea of a classical procedure. You would start with a certain hypothesis and a mathematical statement of what you think the relationship is. The second thing that we do when we teach them is to how to regularize the data. We see that from knowledge of physical chemistry, we can see that we can scale the boiling temperature with the appropriate critical temperature. And that scales the value from numbers from around 0.7 to 1, making the numbers smaller and easier to manage, but also gives them another handle towards the correlation. At the end, of course, they have over 6,000 data points, so they have to choose a subset of them. We suggest that taking 100 random numbers might be useful. We deal with the matrix multiplication problem and just mentioned that this would be the way to solve the minimum likelihood problem. In fact, the students at this point are not so able in terms of mathematics. They're still in the process of learning the mathematics of these problems. So some of these matrix multiplications, manipulations, and the solution is provided to them. They're told that this is the way it works, and later on in your Chem course and your math course, you'll see the exact details of this. They're just told that this is a way to obtain the results. And they actually do that, and we'll see some of the results later on. But then the third task is the important one that's related today. And we suggest that they use an artificial neural network. And here's where MATLAB fits in very nicely, because MATLAB has a built-in optimizer of neural networks, and I'll show you an example of that later on. Interestingly, there is no assumption to be made with respect to the mathematical structure or the correlation. This is an important point to make. Features, which are the inputs, are the eccentric factor and the molecular weight, and they're just simply picked up by an inference, and we saw that they were plausible inputs. Again, to make things at least fair, we train the problem with 100 randomly selected points. And we use the artificial neural network encoder of MATLAB. We guide them to use 2 hidden layers and a tangent sigmoid transfer function. And so that simplifies a little bit the problem, gives them some initial handles to start working. The weights and biases are optimized directly by a Levenberg Marquand algorithm. And in this small cartoon I'm showing you, basically input and output is the only things that we give the problem. The results are quite satisfying. In the left, you have the results which come out of the multivariate or the double linear approximation. The dots correspond to the numbers, the values in the data set, and of course the red surface corresponds to the result of the correlation. The correlation is not very, very good. There is some deviation in the data, and that is expected. But the shape of the curve, of course, in the multivariate is just a flat line. There's no, we're just again fitting a straight line in 2 dimensions. Interestingly enough, with the artificial neural network, it captures a little bit more of the shape of the surface. The R-square improves, and the average absolute deviation also improves. And just that as a side comment, it's just interesting to point out that this is the this is the range of the absolute average deviation that one finds in professional, if you want to call it that way, correlations, or in most engineering correlations. So a fit of this quality is extremely good. So I'm going to show you how this looks in the MATLAB and the MATLAB world. This is a live script, which I'm happy to share with you. And that just simply shows basically the solution, our final solution, or I should say probably a nice solution, because some of the solutions of the students are probably a little bit less refined. There's a first task, which is importing the data, which we can do again with MATLAB structures. And you can see that this list goes on and on and on with enormous amounts of data, which is very hard to process, at least visibly. The first thing that we do is a linear correlation. And doing a linear correlation is basically a very simple, fit that is done in MATLAB. And we can get the correlation coefficient, which we can see that is not particularly good. If one wants to try with the eccentric factor and do a similar thing, again, they see that there is some sort of relationship, but it's not a nice fit, and it's not. There's something more to this than just a linear fit. And this is where the multivariate regression comes in. We suggest then to try to do this as linear in both of these variables, see this, how this fits. And the coding of this, again, we provide helps of that, and it's reasonably simple. I mean, it's basically done on matrix manipulation. The correlation coefficient improves, and as you see, as we saw before, the fit is reasonably good. So here's where we use the artificial neural network. We manipulate some input data, we have some output data, and we provide the students with the code. And believe it or not, the code is just basically these lines. There's an input data, target data, basically a training function, and a fitting of the neural network. I'm just going to perturb this just a second, so you can see real time what it takes to solve the neural network. It's already been worked out and solved, and we can see that the correlation coefficient is in the order of 0.89 and an absolute deviation of 2.2, which is extremely good. So, ending with the conclusions, this exercise has been extremely well received by the students. They actually, it looks challenging, but it's not. And they come back asking for more material to expand their understanding of machine learning. And it's not surprising, because machine learning is now a hot topic. All our employers are looking for data skills in our students. Interestingly, the example can be expanded more. You can look at more refining these correlations or using other correlations, although I might say that the machine learning correlation is already quite good. It's really hard to improve on it, even if you start moving all the levers and buttons. Some people have asked me about converting the exercise to Python, and I might say it's very straightforward to do that also. And in general, we've seen that machine learning has crept up in a large number of the final year research projects, and has proven to be extremely popular topic. And therefore, we're very happy to be supportive of this. Since, in fact, there's a final year elective in machine learning in process engineering, which is also now being developed to also help the students at the end of the career. So thank you for watching. If you have other questions, please direct them to me. There's more details in the final publication we did in Journal of Chemistry Education. I'll be around if you need to ask me anything. Thank you for listening.